Welcome to VLab Solutions. Ever wondered how computers understand human language? The answer lies in word embeddings and Word2Vec. This technique is a cornerstone of natural language processing, and it's all about translating human language into a format that machines can comprehend. Word embeddings are fascinating. They represent words as numerical vectors, capturing their meaning in a way that's digestible for computers. Imagine each word as a point in a multidimensional space, where the position and distance between points reveal their semantic relationships. Similar words cluster together, while dissimilar ones are farther apart. This spatial representation of words is what we call a word embedding. And how do we create these embeddings? Enter Word2Vec, a popular method for generating word embeddings. It's an algorithm that predicts the context of a word within a sentence. By doing so, it learns the meaning of the word, encapsulating this understanding into a dense vector of floating point values. These vectors, or embeddings, are what our machine learning models use to understand our language. Word2Vec has two main architectures: continuous bag of words, or CBOW, and continuous skipgram. CBOW predicts the word in the middle of a sentence based on the surrounding words. It's like trying to fill in a missing word in a sentence, using all the other words as hints. On the other hand, the skipgram model does the opposite. It uses the current word to predict the surrounding words in a sentence. It's akin to guessing the context in which a word might appear. Both these models are powerful, but they have different strengths. CBOW is faster and works well with frequent words, while skipgram is slower but more accurate with rare words or phrases. So, in essence, Word2Vec allows us to transform words into a mathematical language that computers can comprehend. It's like teaching machines a new language, but instead of words and grammar, they're learning vectors and dimensions. And with this newfound understanding, they can help us perform tasks that involve human language, from sentiment analysis to chatbots to search engines. The world of Word2Vec is a fascinating one, and we are just getting started. Now, how do we convert words into these numerical vectors? Well, let's dive into it. The magic happens in the embedding layer of our neural network. This layer is designed to take in integers representing our words and output a dense vector for each of them. Each word is thus converted into a numerical vector, a process known as vectorization. These vectors are then averaged out. You may ask why we do this. The reason is simple. By averaging the vectors, we can condense the information from multiple words into a single vector. This helps to maintain the context and semantic meaning of the sentence as a whole, even though we're dealing with individual words. So, to sum it up, we start with our words, convert them into numerical vectors with an embedding layer, and then average out these vectors. This process of vectorization is the first step towards teaching our computers to understand language. Let's delve deeper into the skipgram approach and the concept of negative sampling. In the Word2Vec model, skipgrams are a way to create training examples. We start with a sentence and select a target word. Then we generate pairs of this target word with surrounding words based on a defined window size. For instance, if we choose a window size of 2, we pair our target word with words 2 places before and after it in the sentence. This gives us the context pairs we need for training our model. But why do we call it a skipgram? The answer lies in the flexibility of this approach. The skipgram method allows us to skip over some words in our window, generating a diverse range of context pairs. This skipping not only increases the robustness of our model, but also helps it capture a wider range of semantics. Now let's move on to negative sampling. If you're thinking this sounds somewhat pessimistic, don't worry. It's actually a clever trick to make our model training more efficient. In a perfect world, our model would learn from all words in our vocabulary for every training example. But in reality, this can be computationally expensive, especially with large vocabularies. Negative sampling comes to the rescue by selecting just a small random sample of words to update the weights for each training example. These words are selected regardless of whether they're the correct context words or not. So how does this help? Well, even though our model isn't learning from all words for every example, it still gets a good grasp of the word relationships over many iterations. The beauty of negative sampling lies in its balance of computational efficiency and learning effectiveness. With skipgrams and negative sampling, we're preparing our model to predict context words more accurately. So next time you're working with Word2Vec, remember, skipgrams help capture a wider context, and negative sampling keeps your model training swift and efficient. Let's keep exploring the exciting world of word embeddings. Now that we have our skipgrams and negative samples, let's move on to training our Word2Vec model. The first step in training the Word2Vec model is preparing the training data. This process involves downloading a text corpus. A text corpus is just a fancy term for a large and structured set of texts. For instance, you could use a collection of Wikipedia articles, a compilation of novels, or even a bunch of tweets. The key is to select a corpus that's representative of the language usage you're interested in. Once we have our corpus, we'll need to pre-process it. This typically involves removing any irrelevant data, like HTML tags if you're using web pages, and converting all the text to lowercase. We'll also need to tokenize the text, which means splitting it into individual words or tokens. Now, with our pre-processed and tokenized text, we're ready to move on to the actual training. To train our Word2Vec model, we'll first need to define it. In our case, we'll be subclassing the Word2Vec model. Subclassing is a programming concept that allows us to create a specialized version of a parent class. By subclassing the Word2Vec model, we can customize it to better fit our specific needs. Next, we'll need to specify the loss function. The loss function measures how well our model is doing by comparing its predictions to the actual results. For Word2Vec training, we typically use a function called negative sampling loss. This function is specially designed to work with the negative samples we generated earlier. Now, with our model defined and our loss function specified, it's time to compile the model. Compiling the model is like putting all the pieces together. It prepares the model for training by setting the optimizer, which determines how the model learns, and linking it with the loss function. Finally, we're ready to train our model. We'll feed our pre-processed and tokenized text into the model and let it learn. During this process, the model will make predictions about the context of words and adjust its internal parameters based on how well it's doing. This iterative process continues until the model's predictions closely align with the actual context of words. And voila, we've now trained our Word2Vec model. But remember, training the model is just the first step. After training, we'll need to evaluate the model to ensure it's accurately capturing the context of words. We'll also want to explore the word embeddings. It's learned to see what kind of relationships it's discovered. By training the Word2Vec model, we're teaching it to predict the context of words, thereby understanding their meaning. Through this process, we're transforming words into numerical vectors that capture the essence of their meaning. So let's dive into the world of Word2Vec and start speaking the language of vectors. We've trained our model. Now what's next? The next crucial step after training the Word2Vec model is to explore the trained embeddings. Now you might wonder, what does it mean to explore these embeddings? Well, it's about understanding how our model has learned to represent words as vectors in a multidimensional space. Each word in our dataset has been transformed into a numerical vector, which is its embedding. But these vectors are more than just random numbers. They are representations of the word's meanings, learned from the context in which they appear in our dataset. So, how do we examine these embeddings? One method is to perform an embedding lookup. This is as simple as inputting a word into our model and observing the output vector. By doing this, we can see how different words are represented and compare them. For example, words with similar meanings often have similar vectors, meaning they are close to each other in the vector space. But looking at numbers can be a bit dry. So, another more visually appealing method is to use a tool like the TensorFlow embedding projector. This tool allows us to visualize our high-dimensional word vectors in a three-dimensional space. It's fascinating to see how words that are semantically related cluster together, forming a kind of word map. Furthermore, the TensorFlow embedding projector also allows us to perform operations on these vectors. For instance, we can add and subtract vectors to discover interesting relationships between words. This is how we find analogies like king minus man plus woman equals queen. In conclusion, the exploration and analysis of word embeddings are not just a final step in the process. They provide valuable insights into how our model understands language. With these embeddings, you can now build models that understand language, opening up a world of possibilities. So what did we learn today? We've uncovered the intriguing concept of word embeddings, numerical representations of words that capture their contextual meaning. We delved into Word2Vec, a method that learns these embeddings by predicting the surrounding words of a target word within a context. We learned how to vectorize sentences, turning words into numerical vectors using an embedding layer. We explored skipgrams, defining context pairs based on window size, and the concept of negative sampling, which enhances efficiency. We've also learned how to train our Word2Vec model, defining a subclass model, specifying a loss function, and compiling it. Finally, we looked at embedding lookup and analysis, exploring trained embeddings and visualizing them using tools like the TensorFlow embedding projector. Remember, word embeddings transform language into a mathematical space where words with similar meanings are close to each other. With these tools at your disposal, you're now ready to dive into the fascinating world of natural language processing. Happy coding!